Now we move on towards our next topic, that is the fast Fourier transform. So we learned that the DFT provides the frequency content of a time domain sequence, yet it is extremely inefficient. In 1965, Cooley and Tukey proposed a very efficient algorithm to implement the DFT, the FFT, which is believed to be the best algorithm for the last century. The development of FFT transformed the discipline of DSP, digital signal processing, by making the power of Fourier analysis affordable, and thus is one of the pillars of modern signal processing. So we'll talk about the efficiency, how FFT leads to much more efficient approach in computing the DFTs in the upcoming slides. FFT is not a transform, rather an algorithm to compute DFT. So in fact, FFT is an approach, is an algorithm that computes DFT, but in a much more efficient or optimized manner. So it is a highly optimized implementation of the DFT. It is because of the FFT, the DFT and the inverse DFT become important practical applications. So practical applications means that you'll find the implementation of DFTs and IDFTs in DSPs, CPUs, FPGAs and GPUs. FFT algorithms makes the frequency domain approach based on the DFT computationally more efficient than time domain convolution. We can increase the frequency sorting ability of the DFT by increasing the value of n. So this was also seen in the previous lecture, that when we are going to increase the number of the samples in a given sequence, that is, if we are going to increase capital N, in that case what we are doing is we are trying to more tune the frequency content of that particular sequence. So in this manner, what we do is we are going to get much more refined representation of frequency content of any sequence if we increase n. Note this also requires taking a longer input sample stream xn equal to n. This in turn will require much greater number of operations to compute. So we saw that in case of DFT, because there are n square multiplies and additions, which means that in case if we want to have much more refined representation of frequency content of any sequence, that is, we would have to increase the value of capital N. But this will again increase the computational complexity, because we have to face that n square multiplies and additions. Now, rather than requiring n square complex multiplies and additions, the FFT requires only n log to the base n complex multiplies and additions. So the implementation of DFT in an optimized way, which is what the FFT does, it reduces the number of computations n square to n log to the base to n number of computations. For example, if we talk about, so these are the values that had been taken from the computations that were performed using only DFT and FFTs. So if we observe the table, we will see that if the size of sequence is 8, which means that it will, if the sequence has 8 samples, in that case the DFT is going to perform the complex multiplies and additions in 64 in total. While in case of FFT, this is going to reduce to 24. And the computational effort of FFT compared to DFT is 37.5% only. Now, in case if the value of n increases, so the sequence size increases, so 32. In that case, we have for DFT 1024 multiplies and additions, while for FFT it's 160 additions and multiplies, and thus the computational cost reduces further compared to DFT in case of FFT. On further increasing the size of the sequence, so we can see that the computational effort of FFT decreases considerably, and it reduces to 0.29% for 4096 number of samples. So this is an excellent approach in order to reduce the computational cost that was originally required in case of DFTs. So by using the Fft algorithm on a 1024 points or sample inputs, we are able to reduce the computational requirements to less than 1% or by 2 orders of magnitude of what the DFT algorithm would require. FFT algorithms makes the frequency domain approach based on the DFT computationally more efficient than time domain convolution. So this was also discussed in the previous slide. It makes use of the symmetry and periodicity properties of twiddle factor. So it's, the twiddle factor is the W factor that we had learned in DFT to efficiently reduce or we perform decimation, the DFT computation time. So we learned that the twiddle factor, and we saw this in the previous lecture, that the twiddle factor is going to contribute some values which are repeated in sequence. So that is why they are said to be periodic. And this periodic property of the twiddle factor is taken benefit of, and we perform the we optimize the algorithm of DFT in this case. It is based on the fundamental principle of decomposing the computation of DFT of a sequence of length n into successive smaller DFTs. So we learned that what is FFT? FFT is an algorithm that is going to perform, in fact, it's a divide and conquer method. And what it does is it performs, it decomposes the original sequence into further subsets and furthermore. So the DFT is computed on the final division that is performed. So we learn in the upcoming slides. Now if we talk about 2-point DFT, which is nothing but a fundamental computation unit of radix 2 FFT. So we call it as radix. This method that we are going to discuss today is the radix 2 FFT, and it is the decimation in time. So suppose that we are given a 2-point DFT, which is shown here. So we have xk written as summation from I equal to 0 to 1 or n equal to 0 to 1. So we had been taking n. So it's I, n, and are same. So you can write this as xn as well. So x of n or x of I e raised to the power minus j 2 pi k n divided by capital N. So since we are talking about capital N is taken as 2, it's a 2-point DFT, and then thus we are taking this as 2. And if we look into x0 and x1, which are the two frequencies or the DFT points of the sequence xi, then x0 can be written as x0. If we expand this, we get the sequence x0 as this and x1 as this one. While the terms that are associated with x0, so the exponential terms, so we have e raised to the power 0 here, we have e raised to the power 0 here, and e raised to the power 0 here. So these can be reduced to 1. So we finally obtain the DFTs x0 and x1 as x0 plus x1, and x1 is x0 plus x1 e raised to the power minus j pi. Now since e raised to the power j pi, so e raised to the power j pi can be written as minus 1, and thus what we get is x0 minus x1. Sorry, this was missed here. This is the correct expression. Now what we normally do is we represent the DFTs into a form of flow graphs, which are called as the Fft flow graph or the Fft circuits, and they comprises of butterflies. So shown over here is the butterfly, which has input x0 and x1. So if you look into these two equations, then x0, the capital X0 is equal to small x0 plus small x1. So this can simply be represented by the inputs x0 and x1, which are fed to a summation block, and the output of this summation is capital X0, which is the discrete Fourier transform. While the second expression says that capital X1 is x0 plus x1 e raised to the power minus j pi, which can be written as x0 minus x1, but in this flow graph we can represent x1 as x0 plus x1 multiplied by e raised to the power minus j pi. So this particular figure is called as the butterfly, and combination of such butterfly that we'll see in the 4-point or 8-point FFT leads to what is called as FFT circuit or FFT flow graph. And this particular thing is called as twiddle factor. So in order to make things more simpler, so it may be possible that instead of drawing a bubble here or a circle here, we can simply represent the value of this branch as e raised to the power minus j pi or w. Now if we try to compute the 4-point DFT, so for a 4-point DFT, what we have is n equal to 4, and in this case xk is given by the expression summation I equal to 0 to 3 xi e raised to the power minus j 2 pi ki divided by 4. Note again that we now are talking in terms of I and not n. So since we had been taking for the past lectures this as n, but following the standard that the book to which this is referred, and the book authored by Michael Parker, DSP. So he has taken this notation, and that is why we have taken the same notation from the book. But that can also be written in terms of small n, as we usually have done in the past. So the DFTs x0 can be written by the following series. Likewise, x1 with this series, x2 with this series, and x3 by this series. Now notice that the first thing that we are going to, because we want the DFTs to be simplified further, which will lead to FFT. So the first stage of simplification is that we reduce the terms which corresponds to the exponential to the power 0. So these can be removed, in fact they will be replaced by 1. So we are going to replace these terms by 1. Now the next thing is that if you observe the expressions here, so for x1, so for x1 we see that we have associated with this small x1 e raised to the power minus j 2 pi by 4, which can be written as minus j pi by 2. x2 is e raised to the power minus j pi, and the next term is x3 e raised to the power minus j 6 pi by 4 or 3 pi by 2. So we see that these terms, as we learned in the previous lecture, we can express the exponential terms by vector which rotates by a certain angle. So for the sequence, for this particular expression, we have rotation of this particular vector from 0 to pi by 2 90 degrees, then pi 180 degrees, then 3 pi by 2, which is minus 270 degree. So these vectors, as we have discussed in the previous lecture, rotates in the manner as shown here. So if you look into these vectors, we see that the vector represented in the top figure rotates by 45 degree, and this is of course going to be discrete in nature, since we are talking about discrete Fourier transform. And for continuous Fourier transform, we are going to have this vector rotating in a continuous manner, while for discrete we are going to talk about discrete steps. So the top vector shows the discrete movement in terms of 45 degree steps, while below this the vector rotates at the angle of 90 degrees. So this vector, the bottom vector, this vector represents the vector associated with the power, the exponential terms of x1. So here we have 0 e raised to power 0, which represents the vector along the real axis on right side, and e raised to power minus j 2 pi 1 by 4 represents the vector when it is along the vertical axis upward or positive y-axis. Now the next term e raised to power minus j pi is the vector on the left side on the real axis. So x1 will have the terms, the exponential terms which are associated with it, representing the vector rotating by 90 degrees. Likewise, if you look into x2, now if you the main thing is that the vector, when it rotates from step 0 to, this is 1, step 2, step 3, and then back to 4. So if we are going to have a larger sequence, let's say we talk about 8 point or larger sequences, in that case we are going to get more than 4 expressions. For example, in case of the 8 point DFT, we are going to get 8 terms. x1 will be having 8 terms in case of 8 point DFT. So what this vector uh, conveys is that for values of k, so let me write this. So for values of k equal to 0, so this corresponds to k equal to 0, this is k1, this is k equal to 2, k equal to 3, and if we have more than 4 point DFTs, then in that case we'll be having more terms. So here we have four terms because we are talking about 4 point DFT. For 8 point DFT we'll be having 8 terms, which means that the fifth term, or k equal to 4, so since this is k equal to 0, this term will be associated with k equal to 0. This will be k equal to 1, k equal to 2, k3, k4. So the fourth term will be having the associated exponential term, which would be e raised to the power minus j 2 pi 4 by 4, or this can be reduced to e raised to the power minus j 2 pi. So this exponential term leads to the vector which is nothing but the vector obtained from e raised to the power 0, which means that this exponential and this exponential will be having same value. And we use this idea, this concept, in order to make the subsequent expressions equal to the expressions that we uh, normally face in the previous terms. So this could be explained further. Rewriting these terms, so what we get is x naught equal to x1 plus x2 plus x3 plus x0 in simplified form. Then the next term x1 can be written as x naught plus x1, the same thing that we have here. While now x2, so for x2 we see that we have the exponential term associated with the small x1 e raised to the power minus j 4 pi by 4, which can be written as e raised to the power minus j pi. The next term is e raised to the power minus j 2 pi, and then we have e raised to the power minus j 3 pi. So if you look into these terms, so e raised to the power pi is the vector when it is along the real axis on the negative side, and e raised to the power 2 pi is the vector along the real axis in the positive side, while e raised to the power 0 is the same vector along the positive side on real axis, while e raised to the power minus 3 pi is the vector along the real axis towards left, or negative side, which means that this particular exponential will be corresponding to the vector equal to this exponential. So we can further simplify this and write this term e raised to the power minus j 2 pi 6 by 4 in terms of the term e raised to the power minus j 2 pi 2 by 4, like this. So we have x2 x naught plus x1 e raised to the power minus j 2 pi by 2 pi 2 by 4, and this term can be written in terms of e raised to the power 0 as shown here. So this can be written in terms of this term that's written here. So these terms, this exponential and this exponential become same, and they are same because if you see the vectors, then they lead to the same value. Since we are talking about sinusoids, so sinusoids are going to have repeated or periodically repeating values, and that is why we are getting the repeated values in the further terms, and this is what we refer to as the that utilizes the periodicity of the sine waves. The next term x3 can further be written in the same manner. So we have x naught plus the term associated with x1, the same thing, while x2 is j3 pi by 2. So sorry, this is 3 pi by 2, and we have this term as 3 pi. Yes, this is 3 pi. And what is 3 pi? 3 pi is the vector along the real axis on negative side, and that is why 3 pi is the same vector as is represented by pi. So we have written the same, we have repeated the same expression, the term here, and then we have e raised to power minus j 9 pi by 2. So 9 pi by 2 can be written again in terms of e raised to power minus j pi by 2. So I repeat this again, we in fact, because of the periodic nature of the sine waves, have adopted a simplified representation of these expressions. So we are trying to, we did this in order to have the expressions of the exponential which were uh, difficult to evaluate separately. So for example, if we want to compute DFT, then what we were doing was we were evaluating each of these exponentials separately. But now what we did is we tried to represent them first in the exponential that we have encountered in the previous expressions or terms. So these four sets of equations can further be simplified and written in this form. So now what we did is we have rearranged the terms corresponding to each of these expressions. The even and odd are grouped together. So we have the even terms and the odd terms, x0 plus x2 plus x1 plus x3. And again, x1 can further be written as x0. So if you look into this expression, so x0 plus x2 e raised to power minus j, the term is brought and grouped with x0, the term associated with x1 and x3 are grouped together here, then again in x2, and then again the same thing is adopted in x3. And now further we further simplify this. We see that we have x0 plus x2. So this is again something that now what we are going to discuss is something that will again be an important part of FFT. So we are trying to more simplify things related to DFT. So we have x0 plus x2 here as well as it is present here. Then again x0 plus x2 e raised to power minus j 2 pi 2 by 4 is present here, and again it's present here. This term is here, the term in x1 is also present in x3. So what we do is we first assign, let's say we assign this. Okay, let's further simplify this. So this can further be written as, since we have x1 plus x3, we can take out e raised to power minus j 2 pi by 4 from here, and what we get is x1 plus x3 e raised to power minus j 2 pi 2 by 4. And this can again be simplified by taking e raised to power minus j 4 pi by 4. And this one can also be simplified by taking out e raised to power minus j 6 pi by 4. So what we're left with this particular expression. So we notice that x0 plus x2 is present here, x1 plus x3 is here, x0 plus x2 e raised to power minus j 2 pi 2 by 4 is here and here as well. This term is here and is also present here. So what we do is we assign the we assign certain terms like a, b, c, d, and we call this x0 plus x2 as a. So let us assume this as a, this as b, we assume this as c, and this as d. So now we'll try to represent each of these expressions, the set of the equations that are given here in terms of a, b, c, d, just to make things more simpler to look. So x0 can be written as xa plus b, x1 can be written as c plus d e raised to power minus j 2 pi by 4. Then x2 can be represented in terms of a, since x0 plus x2 is a, so this can be written as a. x1 plus x3 can be written as b. So this gets x2 equal to a plus b e raised to power minus j 4 pi by 4. And likewise x3 can be written in terms of c and d as c plus d e raised to power minus j 6 pi by 4. Now these simplified set of equations can be represented in terms of what is called as FFT flow diagram of FFT circuit. We saw the flow diagram for 2-point DFT, and now for 4-point DFT this can be drawn in this manner. So we have the input x0 and x2. So what we assumed in the previous slide was a was taken as x0 plus x2. So we have shown here a as x0 plus x2. Likewise, we had b, which was x1 plus x3, and c was x2 e raised to power minus j pi plus x0. So we have drawn the same assumptions with the two butterflies on the flow diagram here. And further, x naught is a plus b. So we are going to take the signal from this, the output from this summation, and this summation, which are a and b respectively, are fed to the next summation block to provide us the DFT x naught. Likewise, x1 can be obtained in the same manner, and x2 and x3, and these are all the associated twiddle factor. And we can also notice here that things are, okay, I'll show this, that once you keep on increasing the values of n by power of 2, then we are going to get an increase in this series, or the levels of this this FFT circuit is going to increase by 1. So in case of 2-point DFT, we only had one butterfly, and we were talking about the input and the output only. But in this case, in case of 4-point DFT, we had one more level increased in the intermediate. And likewise, in case of 8-point DFT, we'll be having a fourth level. And likewise, if you look that these butterflies, the rows of the butterfly will also increase. In case of 2-point, we had one butterfly row. In 4-point, we are going to have two butterfly row. In 8-point, we are going to have four butterfly rows, and so on. And these in fact can be represented in the form of matrices as well. So in case of 8-point DFT, we get this FFT circuit as shown here. So we have four butterfly rows, and then we have four levels. So, and there is also a symmetry that can also be observed. If you look into this figure, so this figure, if this seems to be have been copied here. So this part is very similar or exactly what we have written, or we have drawn in case of 4-point DFT. And again, the same thing is drawn here. Then a symmetrical and thing is going to be followed, since we start from the first level as e raised to the power minus j pi, the next is e raised to the power minus j 2 pi by 2, then third will be having e raised to the power minus j 4 pi by 4, and then again we have e raised to the power minus j pi by 2, we have e raised to the power minus j pi by 4, then we have e raised to the power minus 3 j pi by 2, then we have e raised to the power minus j 5 pi by 4 in the third level, and so on. So in matrix form, we can represent DFTs. So notice that this is the representation of DFTs. So DFT can be represented as follows, and this can be generalized to what this matrix W, we call this matrix as W or D matrix or the twiddle factor matrix. For n-point DFT, we can have this particular matrix represented by following terms, where W stands for twiddle factor. And what FFT is going to do is going to reduce the representation of the factors within these matrices. So using FFT algorithm, many of the exact same multiplications are performed repeatedly. FFT makes use of the periodicities in the signs that are multiplied to perform the calculation. The FFT algorithm organizes these redundant computations in a very efficient manner by taking advantage of the algebraic properties in the Fourier matrix. So Fourier matrix is the same thing that we have in the previous slide. The FFT takes the Fourier matrix and factorizes it into several sparse matrices. So this can be confirmed from the SFG, the flow graph, and the equations that we discussed just. And what we are doing is we are trying to perform a sort of divide and conquer approach. So what we are doing is we are factorizing the main matrix first into sparse matrices and further into small matrices. These sparse matrices have many entries that are equal to 0. This way FFT attempts to solve a series of smaller problems very quickly, as opposed to trying to solve one big problem, which is generally more difficult. The FFT algorithm takes a divide and conquer approach to solving problems. Oh, there's a correction. For example, an FFT of size 64 will first be decomposed into two data sets of 32. These data sets are then themselves decomposed into four data sets of 16. These four data sets of 16 are then decomposed into 8 data sets of 8, then 16 data sets of 4, and finally 32 data sets of 2. The calculation, so this is what the elementary butterfly looks have. It has two components. So what we are trying to do is we are composing the 64 sequence from the basic butterfly comprising of two elements, and we're going to get the size of the FFT circuits increased depending upon how many levels we are going to incorporate. The calculation on a data set of size 2 is simple and inexpensive. The FFT then performs a DFT. So what we are finally doing is the FFT algorithm is going to decompose this is the decomposition that is being performed by FFT, but eventually or finally you will have to apply DFT to these two terms. So the FFT then performs a DFT on these small data sets. The results of the transforms of these multiple stages of data are then combined to get the final result. So this is enough for today. If you have any questions, doubts, you can ask me or post me on my email ID or classroom privately. Thank you.